In this next video, we're going to explore how we can build on our existing understanding of how to find the gradient of a tangent to a curve, and look at how we can find the gradient of a normal to a curve. So we can see here that this is the normal line to a curve, which is at 90 degrees, which is what we've got here. The normal line at a point on a curve is the line perpendicular to the tangent line at that point, which is what we've got here. So here's a fairly straightforward question. Write an equation for the tangent line to the curve fx equals x squared plus 1 at the point 1, 2. So I suggest you pause the video here and have a quick go at this question. So in order to work through this, I've put the graph on here. We wouldn't normally do that, but we've got the tangent line to the curve at x squared plus 1. So in order to find the gradient of this function, we're going to find the derivative using the power rule here, which gives us f dash x of 2x. The gradient is going to be the derivative at the point x equals 1, because that's where we've been asked to find it. So we substitute 1 into f dash x, and we end up with 2 times 1, which gives us the gradient of 2. So we know that the gradient is going to be 2, but we've been asked to find the equation up here. We know the gradient can be found using this formula, and just by rearranging it we can find the equation, because we've got y1, which is going to be up here, 2, we've got x1, which is 1, we've got the gradient, which is 2, so we can just substitute in our values, and we could expand that further if we wanted to, but that is the equation of the line, of the tangent. What about if we have some questions like this? So again, just try and spend a few minutes having a go at this yourself, and then I'll talk you through how to approach these. So the first one then, the normal line to the curve fx equals 2 root x when x equals 9. The classic technique here is to actually give you the question with a root. The first thing you're going to have to do then is convert this into a power of x. So root x is the same as x to the power half. So again then just apply the power rule and the constant multiple rule to end up with the derivative of x, f dash x, which gives you x to the power negative half, or 1 over root x. Again, to find the tangent, the gradient of the tangent, we need to find f dash x when x equals 9. So all we're going to do here then is find f dash of 9, which is going to be 1 over root 9, which is the same as 1 over 3. So we've got the tangent, but the normal line is what we've been asked to find. So remember, it's at right angles, it's perpendicular to the tangent, so we're going to use here the formula m1 m2 equals negative 1. Conversely, you might want to think about it as the negative reciprocal. However you want to do it, if the gradient of the tangent is 1/3, the gradient of the normal is negative 3. Once we've got the gradient then, at the moment we've got the x-coordinate and the gradient. What we need to find is the y-coordinate. So to do that, substitute 9, which is our x-coordinate, into our original function, f of x. So we're going to substitute in 9. We're going to get 2 root 9 equals 6. So now, again, we're in a position where we've got y1, we've got x1, and we've got the gradient. So that's going to give us our equation. Again, if we wanted to, we could expand that further. Question C then, a little bit harder. First of all, again, we've got the denominator as x squared, so the first thing you want to do is change the power here to negative 2. So we're going to take the derivative of x here by just using the power rule here for both of these. So obviously this is x to the 1, 1x to the power 0. Similarly here, 27 over 2, x to the power negative 2, bring the negative power down, and then x to the negative 2 minus 1 becomes x to the power negative 3, or x over 3. So we've got our gradient function here, f of x, and we want to find the gradient at the point where x equals 3. So again, just substitute in 3 for f dash x to find the gradient of the tangent. So again, just substitute that in there. We're going to end up with 0. So this is slightly unusual here. We've got a gradient of 0, so think about what that means for the tangent. If we have our x-coordinate is 3, we can find the y-coordinate by substituting that into our original function here, which gives us 9 over 2. The normal line is x equals 3, and the tangent line is y equals 9 over 2. It's slightly unusual, but you can see here that we have found a tangent initially. So we found the tangent here for f of 3. We can see that at this point, our tangent, the gradient of our tangent is 0, which means we've got a flat line going through here. The normal at this point must go at right angles through this point 3. So if it's at right angles through this point, we know this is the line x equals 3. Part D then, the final one. Find the tangent to this cubic, which is really going to challenge you a little bit here because there's lots going on. So we've been asked to find, or it tells us to find the tangent to this curve that is parallel to the tangent at 4, negative 21. So let's try and unpick this because there's quite a lot going on. So here's our function. Fairly standard principle by now then. We're going to try and find the derivative, which is going to enable us to find the tangent at a point. So here's our function, straightforward, should be getting the hang of this now, using the power rule and the constant multiple rule to find the derivative of that, f dash x. We've been asked to find the tangent, which is parallel to the tangent at 4, negative 21. So the first thing we're going to do is find the gradient here. So f dash x, we're going to substitute in 4, which is going to give us the gradient, which is 11. So we know that the gradient of the tangent parallel to the tangent at 4, negative 21 is going to be 11. Again, you wouldn't necessarily draw this, but just to give you a rough idea, we can see that we've got a, here when x equals 4, we can see there's a curve with a gradient here, and somewhere over here there's going to be some curve with the same gradient. So in this instance, what we're going to set up is essentially a quadratic. This is our gradient function, and we know our gradient function equals 11. So this is just going to give us a quadratic, which we can then solve, and you'll end up with 2 values of x. You'll notice that this value is the one that we've been given in the question. It asks us to find the tangent, which is parallel to the one at 4, negative 21. The only other place, so if this is 421 over here somewhere, parallel, we're going to be at negative 2 up here somewhere. So those both have the same gradient. So once we've got that, then we can find the y-coordinate at negative 2 just by substituting it back into our original function, which is going to give us a y-coordinate of 21. Now we're just going to substitute that into the same equation that we've been using earlier, y2 minus y1 equals mx2 minus x1. And again, the y-coordinate we found here, we've already got the gradient, which is 11, and the value of x2, which is 2.